from the last lesson, you may remember we derived the full Bernoulli equation involving both gains and losses. So pump gain, HP, head loss, HL. So P1 over gamma plus V1 squared over 2G plus C1 plus HP equals P2 over gamma plus V2 squared over 2G plus Z2 plus the head loss. And we also derived a formula for the head loss involving this friction factor F. So my head loss is F, length over diameter, V squared over 2G. So we're going to need these equations for today's lesson involving laminar pipe flow. So we're going to restrict ourselves to the laminar case where the Reynolds number is less than 2,000. And basically what we want to do is figure out how to find this value of F for that scenario for laminar flow. So way back about 10 lessons ago, we solved the Navier-Stokes equations for fully developed pressure-driven flow in a pipe. Ended up with a velocity profile, Vz, so Z going down the length of the pipe as a function of the radius of r squared minus r0 squared, radius of my pipe r0, divided by 4 mu, times the pressure gradient dp dz. Now my pressure gradient, I can relate that to head loss, basically again through Bernoulli's equation, like we did last lesson. So dp dz, remember for these coordinates, cylindrical coordinates is how I derived my velocity equation. So z in this case is L, it's not height, it's the L length of my pipe. So dp dz is delta p over delta L, and then delta p for Bernoulli's equation is gamma times my head loss. So I can replace dp dz with gamma times HL and get that as my velocity profile. What I can now do with my velocity profile is relate all these constants into one constant, Vmax. I know Vmax goes right down the center of my pipe, have that nice parabolic profile. So at little r equals 0, I have just that velocity Vmax, and I can basically take that value of Vmax, or 0, radius of my pipe squared, times gamma times HL, divided by 4 mu L is what it ends up being through all these constants. And then usually I'm dealing with a pipe diameter, not a pipe radius, so simply change radius to diameter, divide by a factor of 2, then squared. So I end up with Vmax is d squared gamma HL over 16 mu and L. And then if you use a flow rate relationship, you can find the flow rate, and with that you can find the average velocity. Average velocity is flow rate divided by area. And so this Vmax value ends up being twice the average velocity. And my average velocity is what we've been calling V for the last few lessons. So every time you've seen a V, that actually represents average velocity. So I can just write that simply as V. And then what I can do now is take my equation over here, solve this guy for HL, and get that HL is 32 viscosity mu, velocity V, length L, divided by specific gravity gamma and diameter d squared. And that's an equation for head loss in the case of a laminar pipe. If I wanted to find the head loss through a laminar pipe, I could just simply use this equation that we just derived. However, we saw last lesson there was a 3-step method that we usually use to find the head loss. First thing you do is find the Reynolds number. Second thing you do is find the value of F. Third thing you do is plug it into this formula for head loss. F times L over D times V squared over 2G. So we know that this has to be the head loss, but I also know that has to be the head loss. So I can equate this expression to that one. So F L over D V squared over 2G has to equal 32 mu V L over gamma D squared, and gamma is rho times G. So now dividing by all the stuff in front of the F, so divide by L, my L's cancel out, divide by a D, one of these D's cancels out, divide by a V squared, end up with another V on the bottom, divide by G's, they cancel out, 2 times 32 gives me 64, so I'm left with 64 on top, viscosity on top, density, velocity, and diameter on the bottom. But density, velocity, diameter divided by viscosity, that's exactly the Reynolds number based on diameter. So an expression for F for laminar pipe flow is simply 64 over the Reynolds number. So in terms of the two methods, either using this equation or the 3-step method, I prefer the 3-step method for 2 reasons. Number one, the first thing you want to do in a problem is find whether it's laminar or turbulent, because this equation only works if it's laminar, so I want to make sure that that's the case. Once you found that it's laminar, to do that you need to find the Reynolds number. So I already have the value of the Reynolds number, so to find F is a very simple calculation. And then once I do that, plug it back into here to find the head loss. Again, another very simple calculation. The second reason I like it is this equation that I had for laminar flow, nice and easy. That's not the case for the turbulent flow. Turbulent flow, you have to do it the second way. The only way to do it is to do this three-step method, find the Reynolds number, find F, then put it back in there for head loss. So for those two reasons, that's generally the way I do it. So time for some examples. First example, I have oil with a specific gravity of 0.81, kinematic viscosity 7.5 times 10 to the negative 4 meters squared per second, flowing through a 15 centimeter inner diameter pipe at a rate of 0.25 meters per second. Want to know what the head loss is per 100 meters of pipe. So first thing, with wording, a lot of times in these you see a rate. Rate could mean either velocity or flow rate, volumetric flow rate. The way I tell is look at the units. Meters per second, that's velocity. If it's a flow rate, volumetric flow rate, it'd be meters cubed per second. So I know this is a velocity. And then head loss of per 100 meters of pipe, so that's the length of my pipe. So to solve this guy, again, I can use either the single equation for head loss, or I can do the three-step method. Again, that's the one I prefer. The first thing I want to do is find the Reynolds number. So Reynolds number based on diameter. I'm given the kinematic viscosity, so I'm going to use this form of it, velocity diameter over kinematic viscosity. So 0.25 meters per second for velocity, diameter of 0.15 meters, and kinematic viscosity 7.5 times 10 to the negative 4 meters squared per second gives a Reynolds number of 50. This Reynolds number is less than 2,000, so the flow is laminar, which is good. If it wasn't, we wouldn't know what to do yet, because that's the next lesson if it's turbulent. So laminar case, again, because now I know it's laminar, I could use that equation we saw before, but I prefer the simple method, find F, so 64 over Reynolds number, 64 divided by 50 is 1.28 for that, and then plug it into my head loss, the general head loss equation, F, L over D, V squared over 2G. So 1.28 times my length of 100 meters, divided by diameter of 0.15 meters, times velocity squared, 0.25 meters per second, squared, and 2G, 2 times 9.81 meters per second squared, gives a total head loss for this scenario of 2.72 meters. And that is the same answer you would get if you use the other equation. The second example, have a standard garden hose, diameter of 1/2 inch, length of 60 feet. Have water flowing through that at velocity of 5 feet per second. I've given the friction factor of 0.012. So based on that scenario, what is the pressure difference across the length of the pipe, or length of the hose? So this is kind of a standard situation you have at home. You have some sort of pressure at the spigot where the water comes out, atmospheric pressure on where it comes out of the end of the hose. Want to find what that pressure is at the actual spigot in your water lines to produce this velocity of 5 feet per second. So to solve this guy, we can start with the full Bernoulli equation or energy equation, P1 over gamma plus V1 squared over 2G plus Z1 plus HP. That's basically going to be at the spigot, equals P2 over gamma plus V2 squared over 2G plus Z2 plus HL. That's basically going to be at the other end of the hose where the water is coming out. So I want to see if we can get rid of anything in this equation. So first thing we can start with is conservation of mass. So whatever comes out of the spigot has to come out of the end of the hose, can't magically disappear. So m dot in equals m dot out. M dot in, mass flow rate, density times velocity times area, so rho 1 v1 a1. M dot out, same thing but at 0.2, rho 2 v2 a2. I have a constant diameter hose of 1/2 inch diameter the entire way, so area 1 equals area 2. Water is incompressible, so densities rho 1 and rho 2 have to be the same as well. So if both density and area are the same, only you're left with is velocity. Velocities need to be the same, so v1 has to equal v2. So you can cancel those guys out because they're equal. And then I'm given that the pipe or hose is horizontal. So if it's horizontal, no change in elevation, no change in z. Z1 equals z2. So z1 and z2 can go away. And then finally, I don't have a pump here. What's producing the flow is the pressure difference between 0.1 and 0.2. so I can get rid of my pump gain HP, and that's the equation I'm left with. So P1 over gamma equals P2 over gamma plus HL is what I'm left with. I want to solve that for the pressure difference, so multiply by gamma and move P2 to the other side. So P1 minus P2, that is my pressure difference, so I'm going to call that delta P is equal to gamma times HL. And then I know my head loss, HL, is F L over D V squared over 2G. So my total pressure difference is gamma F L over D V squared over 2G. But then gamma is rho times G, so I can cancel that G and end up with a 1/2 rho V squared inside there. So change in pressure is F 0.012, L 60 feet, diameter half an inch, but I want that in feet, so half an inch divided by 12 gives me proper units. And then 1/2 density of water, 1.94 slugs per cubic foot, and my velocity of 5 feet per second squared that gives me a grand total pressure difference of 419 pounds per square foot. Divide that by 144, gives me 2.91 psi as the pressure difference across the length of the hose. So last example for today, we have SAE 10W30 oil, has a kinematic viscosity of 7.6 times 10 to the negative 5 meters squared per second, has a specific weight of 8,630 newtons per cubic meter. That's being pumped through an 8 meter length of 1 centimeter diameter tubing, has a discharge of 7.85 times 10 to the negative 4 meters cubed per second, so that is my flow rate. Pipe's horizontal, exposed to atmospheric pressure at both ends. So based on that scenario, want to find the required pump power to make this all happen. So for this one, the first thing we're going to do is find the velocity through that pipe. So we're going to need it, one thing to find the Reynolds number, and then again to find the head loss. So might as well just go ahead and find that through the flow rate. So velocity V is flow rate divided by area, Q over A. Area is pi d squared before, so velocity is 4Q over pi d squared. So 4 times my discharge, 7.85 times 10 to the negative 4 meters cubed per second, divided by pi and divided by the diameter, 1 centimeter or 0.01 meters. Squaring that gives me a velocity of 10 meters per second through my pipe. So now I can find my Reynolds number, Vd over nu, velocity diameter over kinematic viscosity, so 10 meters per second times 0.01 meters for the diameter, and viscosity of this oil, 7.6 times 10 to the negative 5 meters squared per second, gives me a Reynolds number of 1,316. And then now with that, I can find my friction factor F, 64 divided by Reynolds number, so 64 divided by 1,316 gives a friction factor of 0.049. Then finally find my head loss, F L over D V squared over 2G. So F 0.049, length 8 meters, diameter 0.01 meters, velocity 10 meters per second, square that, divided by 2G, divided by 2, 9.81 meters per second squared, gives a total head loss for this scenario of 198 meters. If I look at Bernoulli's equation for this example, P1 over gamma, P1 squared over 2G, Z1 plus HP, equals same stuff at point 2. I was told that I have atmospheric pressure on both ends, so P1 equals P2. So I can get rid of those guys. Conservation of mass, V1 equals V2. Get rid of those guys. It's total is horizontal, so Z1 equals Z2. So basically, I'm just left with my pump power or pump gain needs to overcome this head loss. So whatever my pump, I just need my pump basically to overcome the head loss of 198 meters that I saw before. So my pump gain is also going to be 198 meters, but again, I want to convert that into proper power units. So power is gamma HP times Q. So gamma for this oil, 8,630 newtons per cubic meter. The pump gain or head loss, 198 meters. And then my discharge flow rate, 7.85 times 10 to the negative 4 meters cubed per second, gives a grand total power of 1,342 watts required for this scenario.